Hi, in this video, I'll be talking about continuous functions in the context of real numbers and how they play an important part in certain theorems. So now we'll go back down to from understanding it in just metric spaces. We'll now talk about it in real numbers, specifically intervals. And why do we want to talk about that? Is because real numbers have very nice properties that allows us to show certain theorems. And in a general setting that we'll talk about much later on, having this example now would be a link. And so let's talk about it by defining what does it mean for a function to be bounded. A function is bounded if there exists a constant n such that the image is always less than or equals to m. And so if we take an interval which is closed and bounded, and f is continuous on this interval, then f is bounded as well. And the proof follows because suppose f is not bounded, then for any n, there will exist a xn within the interval such that fxn is larger than n. Since I is bounded, this sequence xn is bounded. Therefore, by the Blazano-Weierstrass theorem, it admits a subsequence that converges to the number x. And since I is closed, this x must all lie within xi. And since we already know f is continuous at x, fxn must converge to fx. But this is a contradiction because we know that we chose this subsequence to be the following property that is unbounded, but now we say that it converges to fx. So this contradiction proves that f is bounded on the interval. And so now we can also define what does it mean for f to have an absolute maximum, which means there is a point such that this point f, the value of this point at f at x star is greater than all other points in the domain, and it has an absolute minimum if it's less than all other points. But we like to note that even if the function is continuous, it may or may not have an absolute maximum or minimum. For example, fx equals to 1 over x. This is continuous, but it doesn't have the absolute maximum or minimum because it can't reach the point infinity or have a value that equals to 0. And so when can we say that it does have an absolute maximum and minimum? Is when it's continuous on a closed and bounded interval. And this is known as the extreme value theorem, which is very fundamental in proving theorems later on, such as the mean value theorem and more that we have seen in calculus. But we have not proved the extreme value theorem in calculus. So we have to use analysis because it talks about the supremum. And so, let's begin the proof. We consider the range of fi. So the values that f takes acting upon I. And since we know I is a closed and bounded interval, by the previous proposition, we have proven that this set is also bounded. And since it's bounded in the real numbers, there exists a supremum and infimum. And we claim that there exist points that takes these values in the supremum and infimum. So, suppose that x star equals to the supremum of fi. Then s star minus 1 over n is not an upper bound. And hence, you can find a number in the interval such that fxn is between s star minus 1 over n and s star. Since I is bounded, this sequence of xn is also bounded. And by the Blazano-Weierstrass again, you can find a subsequence that converges to x star. Since the elements of x prime it belongs to I in this closed and bounded, x star will also belong to I. Because this is a closed set, and so x star is an element of a closed set. And so because x star is an element of I, f being continuous at x star would imply that the limit of f xnr equals to f of x star. And so we have proven that this subsequence converges to fx star. And because of that, because we know f xnr converges to x, we can conclude that the limit of fxnr equals to the supremum of fi, and this supremum must equals to f of x star. And so this concludes that x star is the absolute maximum point of f in the interval I. And hence the proof for the absolute minimum is similar, but you just need to use the properties of infimum instead and produce a sequence. And so you can see how the sequential criteria really plays an important part when we talk about continuity, because it really simplifies the proof and makes use of basic understanding of sequences now. So you can recap again by rewatching the video about the proof of extreme value theorem. But what I like to note that the continuity of f, the boundedness of I, the closeness of I, and I being an interval in the real numbers are all necessary conditions for the extreme value theorem. And you can easily come up with examples or just look into the textbook to see why these conditions are necessary. And another theorem that's important about continuity in the real numbers is known as the intermediate value theorem. And again, you take a closed and bounded interval such that if fa is less than fb, then there will exist a number. If c is a number between fa and fb, then you know there will exist a point in the interval such that fx equals to c. And so it just says that a continuous function assumes all intermediate values along the interval, on the interval. And this is what it meant by saying that you can draw the graph of the function without lifting your pen. So you can just do it like that. And because this is like fa and this is fb, it takes all the values in here. And so the proof of it is a bit longer than the extreme value, but we shall do it step by step. So we let t be a point in the interval, and we want to show that there exists a point p, element of a to b, such that fp equals to t. So we consider the set fx less than t, that's the condition, for x in a to b, then the image is less than t. And since fa is less than t, a will be an element of e, so e is non-empty. And clearly e is bounded by b, and so there will exist a supremum of e. And because this supremum of e must be less than or equals to b and greater than a, so we can say that p is in between a to b. And by the property of intervalness, that means p is an element of the interval a to b. And so now we'll just show that fp equals to the supremum, the t. And so we just consider for any n, 1 minus pn is not upper bound of e. So you can find a pn and get a sequence in e. There will be a subset of a over b. And this will imply that for all n, this sequence will be less than or equals to t. And if you take limits by continuity, this means that fp must be less than or equals to t. And so now if you suppose it is strictly less than, then you can find epsilon t minus fp larger than 0, and by continuity, there will exist a delta such that when x minus p is close to delta close, then fx minus fp will be epsilon close. And then you can expand out this to say that fx is less than fp plus epsilon. And this is really t, because from here. And since p is in between a and b, if p is less than b, then you can choose a point from in a to b that is in between p and p plus delta, which will imply that fx is less than t. And so, this point x will be inside E, which is a contradiction. Because P is supposed to be an upper bound. And if P equals to B, then FB must equals to FP, which FP is less than T, but T must be less than or equals to FB. So this is again another contradiction. So in either case, P cannot be less than B or P cannot equals to B. And so in either cases, it leads to a contradiction, which means that our earliest hypothesis assumption of Fp being less than T is wrong. And so Fp must equals to T. And hence, we have proven that there will exist a point in the interval a to b that takes on the value fx, where fx is in between a to b. And we can again prove that, use examples to show that the conditions of continuity, intervalness, and the least upper bound property of the real numbers are necessary conditions. And a corollary of the intermediate value theorem is that if I is a closed and bounded interval, then there will exist a C such that Fc equals to K, where K is in between the infimum and supremum. And that's really applying the extreme value theorem to get this infimum and supremum. And then using the intermediate value theorem to say that any value in between these two, there will exist a C in the interval such that Fc equals to K. And so this is for a closed and bounded interval. But now, and so closed and bounded has another property such that if I is closed and bounded, then the set of Fi's is also a closed and bounded interval. And really, it makes use again from the extreme value theorem and intermediate value theorem. And I'll let you read the proof for yourself because it's really simple to understand. But what we like to note is that this must be a closed and bounded interval for the set to be closed and bounded, for the ring, the image of the set to be closed and bounded. Because if you can think about it, there exist many counter examples that shows that if Fa to B is an interval, then it's not so obvious that Fi will be an interval from A to B, Fb. Because there could be a point that is less than Fa and there could be a point greater than Fb. So you can't really say what the closed and bounded is. But you know that it will be a closed and bounded interval. So this is what it means to be at the preservation of interval theorem. If you are an interval, and now it could be not closed and bounded, you know that your range is also closed and is also an interval. And it may or may not be closed and bounded. And for the proof, again, it's very simple. Because if A and alpha and beta are elements of the image, then there exist points in the image such that alpha equals to Fa and beta equals to Fb by continuity. And so it follows from the Blazano-Weierstrass the intermediate value theorem that any point in between alpha and beta, then there will exist a point C such that f of C equals to K, which then is an element of the image Fi. And therefore, this interval is consumed within Fi, which is a characterizing property of an interval. So Fi is an interval as well. And we're done. So I hope you have seen how we have used continuous functions when we are dealing with real numbers, improving the extreme value theorem and intermediate value theorem. That's all for this video, and I'll catch you in the next one. Feel free to like, share and subscribe, and I hope you have enjoyed this. Bye!